Alright, let's pick up again here. So we talked about asymptotic directions. Now we can talk about the definition of an asymptotic curve, which is what you think it is. It's a curve whose tangential direction, its forward pointing direction, is also a asymptotic direction for the surface on which it lives. So, and of course we assume it's a regular curve, meaning it has non-vanishing velocity. So regular curve is an asymptotic curve if alpha prime is always pointing in an asymptotic direction. There you go. That is the principal curvature on alpha prime is 0. And of course we can relate that to the shape operator and the unit normal because we have this identity we learned back in section 5.2. I think it was lemma 2.1. We've used this a lot. And but of course S of alpha prime dot alpha prime is also K of alpha prime, right? So that means that K of alpha prime is alpha prime prime dot u, and if that's 0, that means that the acceleration of the curve is perpendicular to the unit normal, which is to say that the acceleration is tangent to the surface. So asymptotic curve has an acceleration tangent to the surface, and if you go back you can see that in the helicoid example from lecture 16 where we had L and N both be 0. So the coordinate curves have acceleration tangent to m, and you'll be able to see that those are in fact asymptotic curves. Now, proposition M is minimal if and only if there exist two orthogonal asymptotic directions at each point on M. This claim is kind of in the middle of a paragraph in O'Neill. It's page 244 where he has this, and I've added a little proof here, and there was an error in my previous version of the proof I had to fix, but here it is. The forward direction was fine. If M is minimal, that means that the sum of the principal curvatures divided by 2 is 0, so of course the sum of the principal curvature is 0, so that means that K1 is equal to minus K2. So therefore if we look at Euler's formula for the curvature, principal curvature, we get that. And if that's 0, that must mean that either both K1 and K2 are 0, or that the theta between them is plus or minus pi over 4. So if both K1 and K2 are 0, then every direction's asymptotic. So certainly there exist two. There exist many more than two, but if K1's non-zero, then this being 0 forces that cosine is plus or minus sine, which is to say that theta is plus or minus pi over 4. And so for those two different directions, you've got pi over 2 between them, separating them, right? So that's the forward direction of the proposition. The reverse direction, see my previous proof, I lacked squares, and there's just not enough space to fit the detail in here, so I wrote it out separate. Here it is. Conversely, suppose that there exist asymptotic directions that are perpendicular, all right? We seek to show M as minimal. Euler's formula for the principal curvature is this, and we can calculate K1 and K2, the principal curvatures, in view of the fact that K of A1 and K of A2 are 0. Let's see how that works. I mean, you don't have to actually specifically calculate K1 and K2. I'm really just interested in what their sum of K1 and K2 is, and that just kind of fell out naturally in the calculation below. So let's see how it goes. So since they're perpendicular, that means that there's pi over 2 between them, plus or minus. And when you put theta 2 is theta 1 plus or minus pi over 2, it changes cosine theta 2 to plus or minus sine theta 1. And likewise, sine theta 2 becomes plus or minus cosine theta 1. And so when we use Euler's formula, we get, cosine theta 1 squared, sine theta squared 1 here for K of A1, but vice versa, we get sine squared theta 1 and cosine squared theta 1 for the A2, because that would originally be theta 2 and theta 2. But, by this and that, we flip from cosine to sine and from sine to cosine. But that's pretty cool, because then it may finally hit you, the obvious thing right in front of your face, add these equations, and when you do that, you get cosine squared plus sine squared, and sine squared plus cosine squared, of course, otherwise known as 1. And that gives us K1 plus K2 is 0, which is to say that the mean curvature is 0. So there you go, there's a little added value for this go around. There's previously some sort of error. It's not quite right. I mean, in other words, it was wrong. Sorry about that. Anyway, moving on. Moving along. Definition. A ruled surface is swept out by a line moving in R3. So, for example, a plane is a ruled surface. See? Sweep. Right? A cylinder is a ruled surface, right? Because you can sweep out the cylinder by just taking the line around, right? Helicoid is formed when you take this, I'll use a little small thing here. You take a ruling and you just kind of like sweep it like that. And if my motion was right, this would always be parallel to the paper. And so like you just kind of upwardly rotate that line that sweeps out the helicoid. And there are others, of course, but and there's also a this definition is geometrically lucid, I suppose, but there's a formula in one of the exercises that I had worked out. I want to say in terms of there's a specific parameterization that you can give for a ruled surface, which is convenient for when you're trying to prove something about it. So I would encourage you, if you're asked to prove something about a ruled surface, don't necessarily use the definition stated on this page here. Maybe go look up that exercise in the homework where we had that other definition, which I wish I could remember right off the top of my head, but I could go hunting for it, I suppose. If you'll indulge me for a second here, see if I can find it. Where was that thing? So many good exercises. It's hard to... I can't remember if it was in chapter 4 or chapter 5. Monkey saddle. Well, here's the formula for it. A ruled surface, x mu nu is beta of u plus v times delta nu. Delta of u. This is the parameterization of a ruled surface. But I feel like there's another place where this is discussed more fully earlier. But anyway, there is an example of that formula. Okay. Anyway, moving on here. A ruled surface M has Gaussian curvature, which is non-positive. And it's 0 if and only if the unit normal is parallel along each ruling of M. Alright, so since ruled surfaces contain lines, of course the acceleration of a line is 0, which means that the lines are asymptotic curves. And so by lemma 6.4, which we proved in the last video, the Gaussian curvature is non-positive. And let's see here. I mean, every point in a ruled surface has a line going through it too, right? So that's not just some points in the surface, that's all points in the surface have k less than or equal to 0. All right. So next up, suppose that we have a line ruling in M, and that the unit normal is parallel along that ruling. Then that means that the shape operator on the velocity, which by the way is the unit normal evaluated at the curve differentiated, right, is equal to 0, which is to say that the curvature of the, principal curvature L prime is 0, which is to say that alpha is principal, therefore k is equal to 0. Yes. If one of the principal curvatures is 0, then, and since Gaussian curvature is k1, k2, then of course Gaussian curvature is 0. Sorry, I just, duh. All right. Likewise, if the Gaussian curvature is 0, then by lemma 6.4, case 3, the asymptotic curve is the principal. All right. And just a reminder, shape operator of alpha prime is minus alpha prime 0, right? Thus, U is parallel to the ruling alpha. I mean, that's okay, fine. I mean, if we have a curve, if we have a vector field, and we evaluate it on a curve, and we differentiate it at 0, and it's, you know, the derivative of the vector field along the curve is 0. That means that the vector field is parallel along that curve, right? my apologies. All right. Silly application. Actually, this is kind of a neat application. Spheres and a sphere and a torus cannot be a ruled surface because they have positive curvature somewhere or everywhere, right? So it can't be ruled because if you have positive curvature, not a ruled surface. That's pretty cool. All right, so that brings us to geodesics. A curve alpha in M is a geodesic of M, provided its acceleration is always normal to M. All right. So, what's that mean? What's it mean for the acceleration to be normal to M? That means that alpha prime is parallel to the unit normal, I believe. All right, so what does that mean? That means that inhabitants of M, quote unquote inhabitants, feel no acceleration along the geodesic alpha because the acceleration is off-world, right? So you think about M being the world in which the M inhabitants live, the unit normal is off-world. And so the acceleration is in that direction, and yeah. So later we'll learn geodesics like lines in the plane give length minimizing paths on M, and there also are many geodesics through a point of M. In fact, one for each choice of initial velocity. If you take a point in M, you can find infinitely many geodesics that go through that point. One for each direction, in fact. And point 3, since the acceleration is perpendicular to the tangent space, right? That's what we meant by normal to M. That means that alpha prime dot alpha prime, which of course is in the tangent space, has to be 0. But on the other hand, we also know that this is the derivative of, the derivative of alpha prime is acceleration dot velocity, right? So if this is 0, that has to be 0, which is to say that alpha prime is a constant, which is to say that the length of alpha prime is constant. In other words, a geodesic has to have constant speed. So point 4, constant curves are trivially geodesic, but we usually omit them to reduce clutter. And lines have alpha prime equal to 0. Hence, any line which you can find in your surface will be a geodesic. All right. In our current context, of course, of Euclidean, I mean, all of this is based on everything we're saying right now. These are for surfaces which are inside R3, right? And later in the course, we talk about a slightly more abstract concept of geometry, and we'll have to be a little more careful what we mean by geodesic. But anyway, one thing at a time. Let's stick with our explicit surfaces embedded in R3. Yeah. So examples. A plane. Alpha is geodesic to a plane with normal u. That means alpha prime dot u is 0, of course. But we also know, if we differentiate again, that the acceleration dot u is 0. So the acceleration must be collinear with u, which is to say that alpha is a line. So the only geodesics in a plane are lines. All right. Spheres. The geodesics are great circles. A great circle is formed by the intersection of a plane through the origin and the sphere, given constant speed parameterization, of course. That's another kind of funny thing about geodesics. If you reparameterize them to give them non-unit speed, then it's not a geodesic anymore. So the concept of geodesic is not reparameterization friendly. Like, you got to stick with the given unit speed parameterization if it actually is going to be a geodesic. So here's a picture of my attempt at a picture of the great circle on a sphere. For a cylinder, the geodesics have the form alpha of t is r cosine of at plus b, r sine of at plus b, and then ct plus d. Here a, b, c, and d are constants. So like some special cases, if we put, you know, if we just put a to be 0, then we'll get like r cosine b, r sine b. That gives you like a particular point in xy. And then if we let this vary, it just makes z go up and down, right? So if I have a equals to 0, it gives us sort of like if vertical lines on the cylinder, right? If you have, on the other hand, if you make, say, c be 0, and you let a be non-zero, then you're going to wrap around the cylinder. And if a and c are both non-zero, then you get something that's kind of more like, well, like this. All right. So if this is my come on, work. Oh, it's too humid in here. My paper's not. All right, so this would be an example, if I could get it. This would be an example of a geodesic on this cylinder. So that's, you know, things like that. Things that are, when you lay the cylinder flat, they're aligned. They actually wrap. When you wrap that plane into a cylinder, those turn out to still be geodesics. Now that's not a proof of why it's a geodesic by any stretch of the imagination. It's just an explanation for how to understand that kind of curve. It's something like that. Again, a equals to 0 gives you a ruling, and c equal to 0 gives you a circle. The proof that those are all the geodesics is on the next page here. So, like, here it is. And this calculation is not too hard. I think it's worth going through. So, suppose we have a curve on a cylinder. Then we can write that in terms of, well, it has to have r as a constant, but in general, theta and h could be functions of t. So that's like an arbitrary curve on the cylinder if you think about it. Now, the acceleration has to be in the unit normal direction, right? So this is the acceleration. It's going to be the second derivative of that, second derivative of that, second derivative of h. Of course, this is just minus sine theta, theta prime prime, and minus cosine theta. Oh, it's more than that. Excuse me. We'll get to it, but I forgot this product rule for the second derivative. H prime prime. I can't get that wrong. Okay, but anyway, this has to be equal to the unit normal. And so if the unit normal just has x and y components, then it must be that h prime prime has to be 0, which is to say h is cd plus d integrating twice, right? Okay, so that's good. On the flip side of things, we also know that the velocity is this, and it's a geodesic, right? So it has constant velocity. So that gives us that when you calculate the length of this, we get, well, h prime is c, by the way. We get r squared theta prime squared plus c squared is constant, right? And so you can just move this, you can absorb this constant into the other constant and call it constant without the underline. So r squared theta prime squared is equal to constant, which then why not divide by r squared and call it constant again? Here, I'll call this one constant tilde. See, ooh. And now that's that's constant tilde divided by r squared is constant. Anyway, oh, square rooted, oops. Anyways, so the point is, eventually, sort through this, you just have theta prime as a constant. Oh, but that integrates to theta as at plus b, which gives us that's a geodesic. Right, so at least all of those are geodesics. And I suppose, if you want to be fussy, have I proved that those are all the possible geodesics? Maybe not quite, but not far from it. All right, so that's pretty neat. Proposition: if a unit speed curve alpha lies in M, the unit speed curve alpha in M lies in a plane P everywhere orthogonal to M along alpha, then alpha is a geodesic to M. So, okay, so if it's unit speed, right, that means that the acceleration is perpendicular to the velocity. But let's see here. What else did we know? It's the curve lies in M, but it also lies in P, right? So let's see here. So since it so both alpha prime and alpha prime prime both lie in P, right? And as alpha prime is tangent to M, of course, that means that alpha prime prime is orthogonal to M, right? Which means that alpha is a geodesic, right? Because the acceleration is in the same direction as the unit normal. Application: meridians are geodesics to a surface of revolution. I want to say parallels are too, because if I take the plane which is perpendicular to the axis, goodness, I think that the curve of intersection that it slices is I want to say that the tangent to that direction is always, well, I mean, of course it's parallel to the tangent space of M, but I don't know, it bothers me I haven't also written parallels here, but meh. But anyway, this is of course a nice result, and you can see a lot of geodesics using this this proposition. If you think about, if you can think about a surface and you can think about finding a plane that slices through the surface in such a way that what? The plane is everywhere orthogonal to M. See, that's not, you take an arbitrary surface, right? And you take an arbitrary plane. So let me just foolishly attempt a picture down here. So here's my arbitrary surface, right? And so this is my M, right? And then I take a plane, take any old plane, and, maybe it's up here in it. Right, so the point is the normal to the plane is kind of like, as I'm drawing it, sort of under the surface, right? It's kind of like down here somewhere. I don't know if I'm doing it justice or not, but it's down there. And so, on the other hand, of course, the normal to the surface, the unit normal maybe is like this, right? So the plane in this case is not orthogonal to M, I could take a different plane, kind of like take that red plane and kind of tilt it like that, and then that might give me, something more like that, and then if I did that exactly right, then the unit, then the plane would be everywhere orthogonal to M, meaning that, let's see, plane being orthogonal to M, another way you could say that is that the plane contains the unit normal to the surface at each point along its curve of intersection as a tangent vector. So like if this plane is perpendicular to M, along its curve of intersection, then the unit normals to the plane should be tangent to the unit normals to the surface M should be tangent. They should lie on the plane, if it's the right kind of plane, I believe. So that's a pretty strict criterion. It's like not any old plane will meet this condition, right? It's kind of a pain to actually find one. The meridian works because if you take the plane through the axis and think about how it intersects the surface of revolution, the surface of revolution, the unit normal, is pointing like radially out from the axis of rotation, but that's also how we're defining the plane. So the plane contains the unit normal at each point along the the curve of intersection, which is also called a meridian, and as such, this proposition would apply to the plane. I want to say that would. I hate to mess up my picture, but if I took a parallel, oh, this won't go well. I don't know why I'm doing this. I'm messing up a perfectly good picture. But the parallel should be, kind of like, I can't do it justice, but, around like that. And, yeah, I think that also meets the condition because the unit normal, right, it's like, it's always directly away from the axis, which is also kind of like a way I could describe the plane I'm talking about, the one that slices perpendicular to the axis. So the axis is normal to the red plane. And the axis being normal to the red plane is part and parcel of the unit normal to the surface of revolution being tangent to the red plane, which means it meets this condition, which means that parallels to a surface of revolution should also be geodesics, if I'm right, if I'm not misreading something here. Of course, if I'm wrong, explain to me in the comments. All right, and that brings us to, appropriately enough, surface of revolution. So I'm going to stop the video right here and start it again in just a minute or two. Thanks, guys.